In this video, we'll be applying MIPS programming to computing the error checking code on the network interface card NIC that sends frames and Wi-Fi from one host to another host. So when the NIC receives the data from the network layer, it computes the error checking code and it adds it to the frame before it sends it. And the reason the network interface card includes an error checking code in the frame is to ensure that the communication is a reliable one. And this error checking code is called the cyclical redundancy check, CRC. And the CRC is based on the data in the frame, and it's included in the header of the frame that's going to be transmitted. So in this video, what we're going to be first explaining is how to compute how the NIC computes the error checking code, and then we'll move on to the actual MIPS code. Okay, so the protocol goes as follows. As mentioned before, the sending NIC will compute the CRC based on the data and then sends the frame. And as for the receiving NIC, it computes its own CRC, again, based on the data that it received in the frame. Then the receiving NIC compares its own CRC to the CRC in the header of the received frame. If the CRC that the receiving NIC matches the CRC that's in the header, then the receiving NIC declares the frame to be correct. And if the CRCs don't match, the NIC then declares the frame to be corrupted, and it may ask for the retransmission of the frame. So now how to compare the CRC. First of all, keep in mind that the data is a big number, and also it's in binary. And also keep in mind that the sending and receiving NICs have the same generator bits G. So we want to choose the CRC bits such that the concatenation of D and R, which is right here, and that's the symbol, should be divisible by G. So the receiver divides D concatenated with R by G, and if the remainder is not 0, that means there's an error. This property of CRC bits can detect all burst errors less than R+1, R being the length of the CRC bits. And note that burst errors are errors that are next to each other in the data. Okay, now how to concatenate the CRC bits. We concatenate the CRC bits with D. To do that, we need to shift D to the left by R bits, and we shift by multiplying D with 2 to the power R, and then XORing with R to append the CRC bits. So now we want D shifted to the left by R bits to be divisible by G. So D times 2 to the power R, XORing R equal to NG, and equivalently XORing both sides, D times 2 to the power R equals to NG XORing R, and also equivalently, if we divide T times 2 to the power R by G, we want the remainder R. So to reiterate, we want the remainder of the shifted D divided by G. So the remainder is the CRC, and we don't really care about the results of the actual division. As I mentioned before, D is a big number, and it's between 1 kilobyte and 2 kilobytes in size, while G is between 16 and 32 bits. So to do binary division in the CPU using MIPS, we need to bring one word of D from the memory at a time, since it's so big, and perform the special division as shown right here. And we have to read words from the end of the data in the memory going towards the beginning because of how the division is done. And keep in mind also that this division is different than the decimal division implemented in MIPS because we don't do subtraction in the process of dividing. Instead, we're XORing, and that's why we have to implement the special binary division step by step. So our strategy is to use a register to shift into it enough MSB bits from the loaded word of D, and to do the XORing as we'll see in the MIPS program following. So this is the MIPS code for doing the CRC computation that I've just described. So as we can see here in the comments, S0 has the base address of data D, S1 has the length of D in bytes, S2 has the length of the generator bit pattern D, G, S3 has the computed CRC, and as we will see in the code, we will be reading data from memory into register T7, and T8 has the number of remaining bits in T7, and T4 has the address of the next word to read. So here for our first line of code, SRL, T3, S1, and 2, I previously mentioned that register S1 has the length of data in bytes, And here what we're doing is we are shifting to the right by 2 positions to get the number of words. So in other words, we're dividing by 4. So T3 now has the number of words in memory remaining. And in the next line of code, we are adding the length of data in bytes with the base address of data and putting it into the register T4. And then after that, we're adding 0 to register T0, which will later be used as the dividend by G. So now here, if we go under the label read word, what we are doing is we are checking if T3 is less than 1, which means that if it is, that means we are in the last byte and there are no more words. So then we go to the end and declare the context of T0 to be the CRC. So we move the context of T0 to S3, and that has the computed CRC as we defined earlier.
Okay, so now we're going to be explaining what happens otherwise. So otherwise, we're going to be moving to this line of code. So we subtract 4 from T4, and T4 is the index of the bytes to read since we are going backward. So now T4 has the address of the next word to read, and in this next line we are going to load that word into T7. And then we decrement, in this line, we're going to decrement the number of words remaining. Next, we are going to reset the length of the data bits to 32. And we do that because we just loaded a new word. So in the next part, we checks to make sure if we have 0 bits remaining in the register, and if we have no more bits, we need to go and get a new word. And it does that in this line where T8 is the length of the word of data in the register. And next we move to this part of the code, the shift part, which is the main part where we need to shift from T7 into T0. So we'll be shifting the most significant bit from T7 into the least significant bit of T0. To do that, we go to this line of code. So here we shift T7 31 bits into to the right into T5. So T5 has the most significant bit of T7. And next in this line, we will be shifting T7 to the left by 1 bit to get rid of the bit. Next, we will be decrementing T8, and T8, as we said before, is the length of T7. So now we have that bit in T5. Now we want to put it in T0. In order to put it in the least significant bit of T0, we need to shift T0 by 1 to the left. So we do that in this line of code. Now we're going to OR T0 with T5. So what this will do is shift into T0 the most significant bit from T7. Next, we will be checking to see if T0 is divisible by S2, which is G. So we do that in this part of the code. So here we're going to check to see if T0 is less than S2. And if T0 is less than S2, then T5 will be set into 1. And here we're going to check if T5 is set to 1, that means T0 is not divisible by S2. And we go back to, we branch into check. And here we shift another bit to largen it. So we need to check to make sure we have enough bits. Now Otherwise, if it is divisible, we move to this next line of code where we're going to XOR T0 with S2 and put the result in T0. And then we will jump into check, and we're going to keep looping and repeat this until we run out of bits. And when we run out of bits, it will load a new word, and sooner or later it's going to run out of words. So at the end, it's going to jump into ends, and we explained this part earlier.